All right, so in section 13.2, we started talking about logarithms. Today, we're going to talk a lot more about logarithms. We're going to talk about properties of logarithms. So we're going to have a long list of properties.
7 of them?
I don't know how many. We'll see how many we end up with. I don't remember how many there are. We'll just make them up as we go. Well, I know the properties. I just don't know how many there are. We'll write them down. We'll get to them. We'll figure out how many there are. The first one, the first property is just a definition. Y equals log base b of x. What's that the same as? B to the y equals x. All right, so that was our definition. That's what we did in section 13.2. And then from that definition, we need to remember that b has to be bigger than 0, and b does not equal 1. And then after looking at that definition, we discovered a couple things. The domain. What kind of x numbers can I plug into logarithm? Anybody remember? I can plug in some fractions. The numbers we can plug in when you're using a logarithm, you can only plug in positive numbers. You cannot plug in 0. You cannot plug in negative numbers. So when you say fractions, I will agree some fractions, like you can plug in 1/2, but you can't plug in negative 1/2. Plug in some fractions, but not others. And we also determined the range. Range was y is all real numbers. So the only x numbers we can plug in are positive numbers. On the other hand, the answers we can get, the y values we can get anything. We saw that we could get positive numbers, we could get negative numbers, we could get 0. So a few examples of this. I'll start a new page to do some examples. What's the log base 2 of 8? 256. 256 is not correct. 7 is not correct either.
4.
4 is not correct.
It's 3.
It's 3. When we convert to exponential form, this is the same as asking you 2 to what power gives you an answer of 8. 2 cubed gives you an answer of 8. All right, so you can see I plugged in x was a positive number, and y turned out to be a positive number also. All right, how about if I gave you log base 3 of 1/9? Because this is the same as asking 3 to what power will give you 1/9. Why does it have to be negative 2? The negative gives you a fraction. The negative pushes it down to the bottom. And then 3 squared is 2. So there's an example where we still have to plug in a positive number, but our answer can be a negative number. So our range so far we have range can be positive numbers. Range can be negative numbers. And then we got 0 by doing something like this. Log base 5 of 1 is 0. Why is log base 5 of 1 equal to 0? Because that's the same as saying 5 to the 0 power is 1. And anything to the 0 power is 1 except for 0. And we said 0 to the 0 is 5. So that leads us to our next rule. There's nothing special about the number 5 here. You just told me anything to the 0 power would give you 1, and I agree. That's rule number 3. Log base b of 1 is always the number 0. Doesn't matter what base you have, base 2, base 12, base 1,000,006, the log base b of any number, when you plug in 1, you will always get 0. Always. All right, rule number 4. What happens when the base and the number you're plugging in are exactly the same? That's where you get 1. And an example of that would be log base 6 of 6 equals 1, because that's the same as saying the base, which is 6, raised to the 1, is the number we plugged in. And again, there's nothing special about the number 6 there. I could use any number in the whole whiteboard. And I think we had these two rules the other day. I think we listed them, that log base b of 1 equals 0 and log base b of b equals 1. I think we listed those two the other day. Questions so far? I think that's kind of where we left off in 13.2. I think that was our list of rules. Only 3 in the definition. Well, I don't think, maybe I didn't list domain and range as a separate rule. All right, other rules. Remember a while ago, we were playing with exponents. And we said something like b to the 5th times b to the 6th is b to the 11th. When we have exponents and we're multiplying things, what happens to the exponents? They add them. The equivalent rule for logarithms is log base b of m times n is log base b of m plus log base b of n. So notice, log exponents had multiplication on the outside. Multiplication was out here, and we added 5 plus 6 became 11. So multiplication on the outside became addition on the inside. Logarithms are the inverse. So logarithms take multiplication on the inside and turn it into addition on the outside. So that's rule number 5. Log base b of m times n is log base b of m plus log base b of n. Back when logarithms were invented, who invented them? John Napier. A guy named John Napier invented logarithms. At the time logarithms were invented, this property right here was considered the most important property in the whole world. But not now. And here's why it was considered very important. If I gave you two numbers like that, would you rather add them or would you rather multiply them? Add them. How come? For adding, you just go down and carry and down and carry and down. What do you have to do when you multiply? It's like a distributive property. I got to take the 9 and multiply it by everyone, and then take the 2 and multiply it by everyone, and then so on all the way through. And then I got to add it all together, don't I? A lot of work to multiply. Pretty easy to add, right? All right. Well, I'm telling you now, you don't have a choice. You got to multiply those together. Well, here's what John Napier said. John Napier said, I'm not going to multiply those together. I'm too lazy. What I'm going to do is I'm going to take 1, 3, 5, 6, 7, 8 times 2, 4, 1, 3, 2, 9. And I'm going to whack them with a logarithm. And what did this rule just say logarithm did to multiplication? Logarithm turned it into multiplication into addition. So this allowed Napier to find the log of this number and add the log of that number. Well, after he added them, he had to get rid of the log. So how do we get rid of a log? we do an exponent. We do an anti-log. An anti-log would be an exponent. Still quite a bit of work. It's still quite a bit of work to what Napier had to do is he had to build a table of values to find logarithms for numbers. So he had to look up on his table the logarithm for this number and the logarithm for that number. But then he could quickly add the two numbers. And then he had another table which he called anti-logs, and he was able to look up the anti-log and get the final answer for this product when he was all done. Still time-consuming, but saved him a lot of work. As opposed to today, if I asked you to multiply those two numbers, what would you do? You grab your calculator and grab your calculator and do it. Yeah, Napier lived back. I believe Napier lived back in the 1600s, where of course calculators didn't exist. Yet people were dealing with very, very large numbers because most of the science going on at the time was astronomy. So people had large numbers dealing with distances between things, and quite often they needed to multiply those things. So other mathematicians and other scientists who found this property thought this was incredible because it saved them an incredible amount of work in having to multiply large numbers. Today, not so important for us because we have fancy calculators that do it for us.
I mean, he had a calculator back then.
You did?
The abacus?
The abacus? Yeah, but an abacus was limited. This multiplying these two numbers would give you an answer too big for a standard abacus.
That's why you make a bigger.
You would need a bigger abacus.
He had a whole wall.
All right, so anyway, what you're going to do in this section is the directions are going to be write as a sum of logarithms. And I might give you log base 5 of 10x. So it's log base 5 of 10 plus log base 5 of x. Take that log and we split it into two logs. That was not particularly helpful, but maybe you have something like this which cleans things up a little bit. What if I gave you log base 4 of 16y? Well, you would tell me it's log base 4 of 16 plus log base 4 of y. But then you would tell me log base 4 of 16, that happens to be a really nice number. Happens to be 2 because 4 squared is 16. So we can write this as 2 plus log base 4 of y. Questions on that? All right, the next rule. Number 6. We're up to 6 already. Back when we were dealing with exponents, what was our rule when we were dividing? Subtract. Top minus bottom. So again, the rule for exponents was if you have division on the outside, it becomes subtraction on the inside. Logarithms, being the inverse, have exactly the opposite property. Logarithms take division on the inside and turn it into subtraction on the outside. It's the same rules as exponents, just written in logarithmic notation. That's correct. They're really exactly the same rules. Yes, the next one's going to have something to do with exponents. But let's look at this one first. So now the directions would be write as a sum and or difference of logs. So I might give you log base 3 of 9 divided by x. 9 divided by 3, you would just divide 9 divided by 3 is 3. All right, so again, what happens is you have division on the inside. Logarithms take division on the inside and turn it into subtraction on the outside. So the things that are on top, they're going to be positive. The things that are on bottom, they're going to be negative. And then log base 3 of 9 happens to be a very nice number. It's 2. So our final answer would be 2 minus log base 3 of x. What if I gave you log base 5 of xy over z? Okay, so that could be written as log base 5 of xy minus log base 5 of z. The division inside here became subtraction outside there. And then the xy turns into
log base 5 plus log base 5 y.
perfect. Multiplication gets converted to addition. So notice what happens here. The things that were on top, they were positive. The thing that was on bottom, when we got all done, it ended up with a negative in front of it. Questions on that? Actually, the goal is going to be, in a minute we're going to do this, the goal is going to be to go backward. Actually, what's going to be more important is to start with something that looks like this and convert it back to something that looks like that. It will be more important to write things as single logarithms than as sum and difference. So in a minute we'll go backward. And the reason this is more important is this is going to be, having a single logarithm will be more useful when it comes to the next section, which is solving equations involving logarithms. Oh no, that's not the next one, it's the one after that. So that's what we're building up towards here, being able to solve equations. What if I change this one just a little bit? What if I made it log base 5 of x over yz? Log base 5 of x minus log base 5 of yz. And then I have to separate the yz, so it becomes log base 5 of x minus log base 5 of y plus log base 5 of z, and that's almost correct, but there is an error there. The error is, no, this minus was in front of this entire logarithm. So when we split that logarithm, we need parentheses around it, like so. Or, which means we got to take this minus sign and distribute it through. So this is log base 5 of x minus log base 5 of y minus log base 5 of z. So notice it's really pretty simple. Everything that was on top has a positive in front of it. The things that were on bottom have negatives in front of them. So things on top get positives, things on bottom get negatives. Is that a rule? Sounds like a rule. Sounds like a rule. And it's kind of the same rule, isn't it? How, when we were dealing with exponents, how did we get things on bottom? If they had a negative exponent. The opposite, the logarithm rule would be, well, if things have a minus in front of them, they came from the bottom. Kind of the opposite rule. Exponents, they came from the bottom. Sounds kind of mean. I didn't mean it to be mean. I'm trying to be nice. All right, next rule, number 7. We're up to number 7 already. What if I gave you the log base 3 of x squared? Okay, x squared means multiply. So this is the log base 3 of x times x. We can use our addition rule. This is log base 3 of x plus log base 3 of x. What's another way to write log base 3 of x plus log base 3 of x? 2 log base 3 of x. There's 2 of them. So, notice, what happened to this exponent? We started with an x squared. The exponent just moved down to the front of the log. Would it matter if I started with x cubed here? Because then I would have x times x times x, which would be 3 of them added together, which would mean we'd end up with a 3 down there. All right, so there's rule number 7. Log base b of x to a power, the power comes down front. Oh, this one I should have had a little rule over here. This one, of course, n can't be 0. And this one we need to be careful. This rule number 7, if x is a negative number, then p better be a positive number. What happens if it's not? That's a good question. All right, so let's take a look at that. Yeah, they fight and it's ugly. Nobody enjoys it. All right, so what if I give you log base 3 of negative 3 squared? Well, I think you would agree that's the same as log base 3 of 9. Negative 3 times negative 3 is 9. And what's a log base 3 of 9?
2.
That's 2. However, log base 3 of negative 3, what happens if I try to pull that exponent down front? What's the log base 3 of negative 3? What do you mean by nothing? I can't do it, can I? That goes all the way back to the domain thing. What kind of numbers can we plug in for x?
All positive.
Only positive numbers. So, that exponent property doesn't work there, does it? That exponent property doesn't work when this thing in here is a negative number. Gives you problems. So I'm going to change my rule. I wrote my rule wrong. My rule needs to be, x just needs to be a positive number. Can't use negative numbers for x, unfortunately. Alright, so write as a sum and or difference again. Same directions. But now I'm going to give you log base 4 of x cubed over y. Keep going. That's correct. I'm going to do it in 2 steps though. I'm going to write log base 4 of x cubed minus log base 4 of y. Logs take division and turn them into subtraction. And then I'm going to use the exponent rule. What do logs do with exponents? The exponent comes out front. So the final answer would be 3 log base 4 of x minus log base 4 of y. And after you've done a few of these, you do start doing it all in one step. You recognize that the division becomes subtraction and the exponents come out front. But for now, I think it's a good idea to do it in a couple steps here. How about the log base 7 of 6 x to the 5th over
Y to the 17th.
square root of y. Oh, square root of y.
So then you will have 5 log base 7 6x minus log base 7 square root of y.
Ah, now you made a mistake.
Yeah, I know I did.
So this is why we better do it in multiple steps. First off, notice there's multiplication right there. 6 times x to the 5th. What do logarithms do to multiplication? They add them. So this is log base 7 of 6 plus log base 7 of x to the 5th. And then what does logarithm do to this division? Subtracts it. Log base 7 of square root of y. Log base 7 of 6 plus, this 5 comes down front, 5 log base 7 of x. So there's where your mistake was. You had the 5 in front of both of those. But you got to do the multiplication first, and then the exponents. How about this one?
I mean, maybe transfer it to
I can convert it to an exponent and then bring the exponent down. Square root of y is the same as what exponent? It's a positive 1/2. So remembering that square root of y equals y to the 1/2, I have minus 1/2 log base 7 of y. I can take care of that exponent too. So I can get rid of square roots, I can get rid of exponents, I can write everything just as single logarithms. Questions on that? And then we would look to simplify if we could. Unfortunately, log base 7 of 6, that doesn't simplify. If that were, say, a 49 right there instead of a 6, we would say log base 7 of 49 is 2, because 7 squared gives 49. So we look to simplify if we can. Unfortunately, that one doesn't simplify at all. Now, like I said, what we've done so far is good, but really not what's important. What's important is going the other way. So going the other way, the directions will be write as a single logarithm. And this is the skill we will really need in order for doing a process called solving equations. So you might have log base 5 of x plus 3 log base 5 of x plus 2.
So it would be log base 5 x. Sorry. X plus 2.
Correct, and really what we did there is we did 2 steps at once. This 3 right here goes inside, and when it goes inside it becomes an exponent. And then we see we have addition out here. Addition turns into multiplication. So I'm going to add an extra step here just to show it. This is log base 5 of x plus log base 5 of x plus 2 cubed. The number out front goes in as an exponent. And then logarithms take addition on the outside and turn it into multiplication on the inside.
Oh, so that's a dot, not an inside.
That's a multiplication right there. That's a dot, yes. Sorry. Could have drawn a star. I chose to do a dot and then it was confusing. All right, how about 1/2 LOGY minus 1/3 LOG 7? All right, we can do 7. So first off, this is, what is it? I didn't put any base, did I? I just wrote LOG. If I write just LOG, what's the base again? 10. 10. This is known as the... No, that was the other one. ln was the natural log.
Unnatural.
No,
Power law.
common. This is called the common log, log-based.
CL.
All right, so again, what I would do is I would do this in a couple steps. First off,
Log.
that power, that number out front goes in as a power,
Yeah. Divided by.
minus, and that one goes in as a power,
Log. Y.
and then logs take subtraction and turn it into division. You could write your answer that way. That would be perfectly acceptable. You could also write this. This is log square root of y over cube root of 7. You could also turn things into roots, whichever you think is going to be better for you. I will accept either. I wouldn't care if you wrote it as exponents or with roots. Questions on that? All right, how about minus 2 log base 4 of x plus 6 log base 4 of x minus 1 minus 3 log base 4 of x plus 1. How would you write that one as a single logarithm? Well, what are you going to do with the numbers that are out front? There's 3 numbers out front of each logarithm. What are you going to do with those? Bring them in, they become exponents. So this is log base 4 of x to the negative 2 plus log base 4 of x minus 1 to the 6th minus log base 4 of x plus 1 cubed. All right, so first off we take care of all the numbers and we bring them in as exponents. Then what happens?
Then you convert additions,
All right, so my final answer then is going to be log base 4 but what would you do with an x to the negative 2? It would really go down to the bottom, wouldn't it? So the x squared should really be down on bottom. X plus 1 cubed should be down on bottom because it had a minus in front of it. X minus 1 to the 6th goes on top. So again, notice what happened. This one had a minus in front of it from the beginning, and it ended up on bottom. Anything with a minus, these two had the minuses, anything with a minus is going to end up on the bottom. Anything with a plus goes on the top. Exactly the same rule as we had with exponents. Anything with a minus we drop to the bottom. Anything that had a plus stayed up on top. Questions on that? All right, the last thing in this section, and I'm going to steal a couple off this worksheet to make it easier for me. All right, so it says solve for y in terms of x. What does that mean? When I get all done, what should my answer look like? It should be y equals something with a bunch of x's in it. It might not just be y equals x, it's going to be something else. All right. So I think what we're going to have to do is write this as log base 3 of y equals
log base 3
of 6 divided by x. So we combine those two logarithms into a single logarithm. Now, what has to happen? if log base 3 of y equals log base 3 of 6 over x, the log 3's cancel, which is correct, but we're not really dividing by log 3. We can't divide by log 3. What we're really doing is we're converting both of them to exponential form. You can't divide by log3. Log3 doesn't make any sense. It's got to be log3 of something. You can't just divide by log3. But because they both have log 3, and because those things are exactly equal, the things inside have to be exactly equal. So y has to be 6 over x. All right, so you can see where this is going to lead us into solving equations. This is why we kind of cover this section. How about this one? We have log base 10 of y equals. What do you get when you convert this to a single log? Log base 10. Square root of x to the 4th times x squared. All right, so we did a couple steps in one there. First off, we took these numbers that were out front, the 4 and the 2. Those came in and they became powers. And then this addition sign, logarithms take addition and turn it into multiplication. I think we can do better than that, though. What happens when you take a square root and then you do a 4th power? Square root is x to the 1/2. So square root of x to the 4th, you're absolutely right. That's x to the 1/2 to the 4th. We multiply our exponents, that's x squared. So this is x squared and this is x squared. X squared times x squared is x to the 4th. So that whole thing really simplifies down to be log base 10 of x to the 4th. So y equals x to the 4th would be our final answer there. Questions on that?